Am I invisible? So if you heard a song we played before the lecture, you must heard this lyric several times. And well, so something good about abstraction is that the abstraction, well, we say the abstraction create an illusion, but on the other hand, the reason why we want this illusion is because it also hide the detail like the detail of the system after this illusion or say this abstraction. So for example, in the very beginning, we talk about the most common abstraction in operating system for a running program is to create a process. So although you have volume architecture or say volume computers like this, you have processor, you have SSD, you have memory. But if you have the processor, process abstraction, all you need to know, or being a programmer, all you need to know is that you have a virtual memory space. And as long as your code and static data plus your heap and stack can fit into the virtual memory, then your program will be able to run on a volume machine, and the underlying the underlying operating system will help us to schedule this virtual created process, including its virtual memory on the available hardware resource. So being a programmer, you don't have to deal with this complexity that's hidden or say invisible behind this process abstraction. And on the other hand, from the hardware's perspective, we also have no idea what the processor would be, or what the process will be doing, or say from the operating system's perspective, we have no idea what the process is doing if we are in the user mode, because most of the time your operating system kernel or say your kernel handler won't get involved in the program execution. And that's the good thing about abstraction. But today's lecture, in the very beginning, we are also going to talk about this kind of virtualization may potentially create issues when we are doing scheduling. So, but before we talk about the topic that we are going to cover today, we say that to virtualize the one part of the goal of the operating system is to virtualize the processor, and to by virtualizing the processor, one of the most important tasks is to schedule the process. And in the past, in your undergrad operating system, you spend a lot of time learning a lot of scheduling policies. However, we also told you that those policies, like the non-preemptive one, the shortest job first, well, the professor always tell you this is the best, but it doesn't work out. Preemptive one, shortest time to completion. We also say this will give you the best turnaround time, but turns out that it's also not practical. So the practical ones, first come, first serve, or round robin, they all have their issues. Like for round robin, we talk about the saturation problem, where when you have way too many processes, it's almost impossible for your program to get a chance to make progress because the scheduling quanta schedule for each process is just too short for you to warm up to complete your task. So last lecture we talked about a more practical algorithm called multi-level scheduling algorithm, and the spirit of the multi-level scheduling algorithm is that we give different priority queues and assign the an incoming process to different priority queues based on the size of their program. But by size here is the static compile size, or say the memory size of the program itself. And the intuition behind this is because they believe a program with more instructions tend to execute longer. Although this is not 100% true, but later on you will see they have some other way to fix this. So for example, if in the first round you cannot complete your job, your task will be gradually moving to a higher queue. However, but in this way you can also imagine that if you are in a system where you have a larger process, but if we keep having smaller tasks, your larger process may eventually get stuffed. So that's one of the drawback of that, right? And however, it's almost impossible to guarantee everything. So that's why we have a lottery paper like this, because one of the reasons they want to rethinking about scheduling using lottery is because most of the approaches are not flexible responsive, or the overhead running a perfect algorithm is way too high. And more importantly, well, we have way too many good researchers in a way that we write good papers, but nobody really know how they work because no one really know how this mathematics would translate to real implementation. So the lottery has a different view of that, is that, well, every process just hold a certain number of lottery tickets, and the number of tickets you have is corresponding to the importance, or say the priority of your program. And more important program or higher priority program will get more tickets, meaning that they will have more chance to win the CPU resource. And and every time we just randomly generate a lottery ticket to see who would get the share of the process. So these are the two mechanisms that we talked about in the last lecture. But again, you might already have you probably don't like them. However, they are the practical ones, and those perfect ones, they are like what the lottery paper said. They are probably not that practical at all. So today we are going to continue. We are not going to talk about the scheduling policy. However, we want to talk about the thread scheduling a little bit, and when a thread and what happened and what are the issues when we perform multi-threaded programming encounter with the issue, we encounter with the scheduling, and then we will talk about the concept of virtual memory. So one of the paper that we assigned, but we didn't get a chance to discuss last time, was scheduler activation. And scheduler activation is talking about effective kernel support for the user level management of parallelism. So before we talk about this paper, one of the key things that we should before we talk about this paper, one of the key concepts that you should have is that what is user level thread and what is kernel thread? All right, let's wrap in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, definitely a go for group discussion. So now go ahead and start the discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now, oh, this is kind of interesting, huh? So now I'm inviting one of the group to share your thoughts with us. So, okay, raising hand feature is back. So Daniel.
Hi, our group decided it was E4 because for the first one, if you wanted to switch a kernel thread, you have to switch into kernel mode. For the second one, the user level threads aren't distinguishable from the kernel. They're treated as like the same process. And then for the same reason, number 3 is true. So if one thread is blocking, then all of them are, then the whole process may be blocked. And then I remember reading somewhere that the thread library can be achieved without modifying the kernel. And threads are supposed to be
right. So
yeah.
So thinking about that, right? If you are doing something in user level, you definitely don't have to modify the kernel, and that's the spirit of mock. right? So like if you selected to not having a thread abstraction in your kernel, then it doesn't have to go through the kernel, right? It's just a feature that you provide by your library, right?
Yeah.
Okay, cool, awesome. So this question is pretty interesting, and I'm glad you guys discussed. So let me share the discussion. Before discussion, C, C, and D, they are the most popular answer. But surprisingly, after the discussion, almost every group chose, every one of you chose E. So it's an evidence that this teaching method really works out, right? But and I think Daniel presented very good insights about that. So right now, I'm also going to go through the question, the concept of user level and kernel threads again, right? So the concept of user level, well, so we said that, well, so if you remember the paper we read before, right? Like in the era of Unix, there's no such a thing called kernel. No such a thing called threads, right? So the concept of threads becomes available after the paper mock, right? So which means that any earlier design of the operating system kernel doesn't really have the idea of threads. However, people love threads because, as we mentioned before, right, threads is lighter weight, right? So and threads, because we share the virtual memory, so it's easier to achieve parallel programming. So people love the idea of threads, and to support this demand from the application, or say the programmer, what really happened is that, okay, so can we achieve the function of thread without modifying the kernel? And the solution is user level thread. So the concept of user level thread is like this. Well, the kernel is unmodified, so all your kernel can see is just processes. And whenever you create a process, you can potentially call a library, like a runtime library, for example, a pthread library or something. And this thread library itself will maintain a thread list itself. And the thread library itself will multiplexing the execution of these threads, and will maintain a state of program counter and for execution. So everything regarding thread is maintained by the thread library. However, those threads, they are invisible from the kernel's perspective. So kernel only see one process. So what will happen is that, well, the giant process, no matter how many threads we have, is all considered as a single scheduling identity. So when we are scheduling the, okay, Rogelio, do you have a question? Hello?
Sorry, I'm sorry to interrupt you. But what's the difference between the thread list and then the thread that you're pointing to in this image?
No, the thread list is just a list of these small threads, and these are maintained by your runtime library, and they are invisible. So it's your library maintain a table saying that, hey, this process contains this many threads.
Mm-hmm.
However,
Okay.
this library also runs in the user level, so it's part of the application that you are running.
I see. Thanks.
Yeah. Okay. So okay. So the all the operating system kernel, or say the scheduler, would say is this giant process. So it's all or nothing. You can schedule the whole process or retire the whole process, but not saying that I just want to schedule part of it. No, it's all or nothing. So another concept that that to implement threads, and it's actually the concept that, okay, what if we can extend the kernel? So your kernel natively support the idea of threads in a way that, in addition to a process list, you also have a thread list in your kernel space. So your kernel maintains two lists of them. So for each process, they will have a thread list. And when you create a process, not only the process is being seen, you also see the threads inside the process. So in contrast to the user level process, that the operating system kernel is unaware of the user level threads, the kernel threads is that the kernel can control each of the scheduling directly. However, it also means that whenever you want to change the running on your processor, it has to go through the kernel handler or the system call. And the other thing is that because each of the thread is a scheduling identity, so they works individually. However, for user level threads, right, switching the process require kernel. However, once your process is scheduled, which thread gets to run is completely depending on the user level library, and your kernel doesn't get involved. However, on the other hand, if you have a thread that is currently blocking the whole progress of the process, unless the operating system kernel is aware of that, there's no way to resolve that situation. So both of them has their pros and cons, right? And for this question, the answer is that all of them are true. And but how do we resolve the dilemma? Because as we can see, like both of them has their pros and cons. Like the user level thread, it's efficient, it's customizable because everything is in user space. You don't have to modify the kernel. However, for kernel threads, well, it better matches the multiprocessor hardware, and you have more powerful feature provided by your kernel. However, because every time when you need to switch the kernel or request the creation of a kernel, have to go through the kernel, request the creation of the thread, you have to go through the kernel, so it's slower. So so here's the dilemma, right? The conventional operating system is only aware of kernel threads or unaware of all the threads. Can we have some kind of intermediate? So that's the concept of scheduling activation try to propose. So it's trying to resolve the issue that the operating system kernel only provide each only provide virtual processor for a process, because in a conventional operating system, each process can only own one processor. So the concept of scheduling activation is that let's change the processor in a way that provides you a multi-processor. So since the process is given multiple processors, the user space library will have the capability to schedule threads onto multiple processors in this way. So that's the basic concept of schedule activation. So in the beginning of the creation of the process, in conventional operating system, I only give you one processor, one virtual processor. But now in schedule activation, I'm giving you a number of virtual processors. And it's up to your thread library decide which thread gets to run on this virtual processor. So by virtual processor, you can consider a virtual processor as something like a scheduling identity. So you can consider that when you create a process in scheduler activation, each process will be given multiple scheduling identity, and those multiple scheduling identity can be mapped to multiple processors. So so in this way, the user level process can schedule multiple threads on different virtual processors to have them running in parallel. And however, whenever your process feel like you need more processors or you don't need that many processes, you provide some kind of mechanism to notify the kernel saying that I don't need that many processors or I need more processes. Right. So that's the facilities provided by schedule activation. Instead of creating a new abstraction, we instead give you multiple processors in the very beginning, and we don't create a new abstraction code thread in the system, but through this multiple processors given to each process, we can still control the parallelism inside each processes and control the hardware resources used by each processes. So that's the virtual multiprocessor abstraction provided by scheduler activation. So the basic idea is that, well, create the scheduler activation is just a container of multiple processors. And the kernel can request more processor through an opcall. And the opcall meaning that I want, so the thing is that, well, because we have the preemptive multi-scheduling. So when the kernel feel like I want to remove some resource from the current process, or I want to give you more resource, I will create an opcall to notify the user process. And the user process, on the other hand, can use down calls to, or say, you can consider this down calls as some kind of system calls from the user process to the kernel to request more resource, or tell the kernel saying that I don't need that many processor because I actually have this processor idle. So that's the whole idea of scheduler activation. So the whole idea is simple. You just provide a new system call and create a new app. And just instead of giving one processor to a process, you give multiple processors in the very beginning when you create a process, and gradually adjust it when a program is running. So the key difference is the key difference here from a kernel thread is that you don't well, even though your user thread is blocked, the kernel still don't know that. So we don't have to. So the kernel doesn't get involved in the user thread scheduling. However, for the kernel thread, the kernel actually directly control that, right? But that's not the case for scheduler activation. So the scheduler activation was once implemented in NetBSD, FreeBSD, or Linux, right? Because however, the thing is that because again, right, the kernel still have no idea about what the task and the priority of each user level thread. So potentially we may still preempt or say schedule a virtual processor or say like stop a virtual processor when it's running. And what if the virtual processor that we are running right now is actually control the critical progress for a user level thread? So that's the potential issue of scheduler activation. That the scheduler activation still cannot resolve, because again, kernel has no idea about what the thread is doing and the relationship about this thread. And because kernel is completely blind, or say the task of a user level thread is still invisible from the kernel. So even though we give you multiple processors in the very beginning, I may preempt one of the multiple processors that's given to your program. And what if the program is what if the virtual processor that get preempt is the performance critical one? Then the whole scheduling would be messed up. So that's one of the issue with scheduler activation, right? However, it does resolve the issue that, as we mentioned, the dilemma between user level thread and the kernel level thread. So that's why it has been implemented in BSD and Linux. Both are popular, right? So so that's why it's still an important concept. And now the Linux thread implementation actually becomes a kernel thread model, in a way that if you remember in the second lecture, I show you the thread status, the thread status data structure, right? Meaning that Linux kernel is aware of this user levels, aware of the thread that's running on the system, and consider each of the thread as a scheduling identity. So if you are interested, definitely check the Linux thread implementation, and it's now part of the kernel support. And part of the reason is also the Linux is okay to do that right now is because our processors, microprocessor or our computer architecture has been optimized in a way that we support this thread creation and management in a way that we make it more efficient than the past. So that's why Linux is okay to treat all the scheduling identity as tasks, including the threads. So scheduler activation is not in use. However, the concept of scheduler activation is still interesting. All right, so now the second thing we want to talk about is that the system has the ability, has the mechanism to see threads now. So when being a programmer, most of the time, you don't think that the scheduling bothers you. But now I want to tell you, like being a system programmer, sometimes this scheduling would be really annoying. So if you were having experience in multi-threaded programming, or if you had the undergrad operating system experience, this producer-consumer problem might not be that innocent to you in a way that you have a producer thread and you have a consumer thread. And the idea of this is that you have a buffer. The producer can put a number in the buffer, and a consumer can remove an item from the shared buffer. And the key thing is that you cannot have the producer running ahead. You cannot have the consumer running ahead of the producer, and you cannot have them both working on the same one. Right, so those are the issues in a bounded buffer problem. So it turns out that you need to create a critical section in both the producer and the consumer in a way that a critical section, you want to guarantee four of the things. The first thing is that mutual exclusion, as we said, at most one of the process or say thread can in the critical section in accessing an item in a buffer. And the second thing is that progress, right? So one of the main thing about the parallel programming is that we don't want we want a parallelism. So if you have a thread that's if you have a thread that can never make progress, right? Like we can never enter the critical section because of some reason, then that's not a good critical section problem. Right. And another thing is that you also want to have fairness, right? So like the producer consumer, you want them to be in a fairly comparable speed, or say fairly comparable chances to access the buffer. So you cannot have a thread that be postponed indefinitely from entering its critical section. And finally, your solution must be able to accommodate the non-determinism. As we said, you have multiple processors, you have different speed of processors, and each thread or each process, they may run on different speed because of the lots of the situation, right? So a critical section problem must solve for all of these four. So the most naive implementation in the bounded buffer example is that you just use the pthread lock and unlock like this to protect the part of the code that is trying to modify the buffer item, right? So so this code, I would say, from the user's perspective, there is nothing to criticize. However, what I really want to ask you is that, well, how to implement the lock and unlock correctly? So a very naive solution is that, what if we just use spin lock in a way that we have a variable called lock, and we just test if the lock is currently set or not, right? If it's set, then we just keep spinning, right? And if it's not set, then we grab the lock and set a lock value to be 1, and then we enter the critical section, right? Otherwise, your function will be kept in a while loop without doing anything. And when you are done, you just unset the lock. So that's a spin lock solution. And so now I'm asking you, right? A lot of you might already know this is not working, but I want to ask you why this is not working. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now for this question, I do believe we need a group discussion, so go. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so for this question, I'm inviting one of the group to share your thoughts. Okay, Rogelio, you got it. What do you think?
I think our team chose the answer is A, at most one process
Okay.
can enter the critical section. This is what is guaranteed
Okay.
by
So.
Finlock.
Okay. So. Well, let me share the discussion result with you. So before discussion, this is like this. And after discussion, it looks like this. So it turns out that I believe Team Blue have a different answer. So someone in Team Blue, can you share the thoughts with us?
I'm from Team Blue, and our result is option E is right.
Okay, so Team Red, Rogelio, he is the representative of Team Red. They thought A could be guaranteed, but can you give me a case why you guys don't agree with that?
Yeah, I think if the spin lock works well, the option A is right. But the code you showed before, the spin lock is vulnerability because if there are two processes, they obtain the lock, and before the lock was set to 1, they will enter the while loop at the same time. Yeah, the while loop
So you
while
say
log
both of
is
them,
equal to
both
1.
process will be able to enter the while loop at the same time.
Yeah, so this spin lock
Okay,
cannot guarantee.
so that only, okay, so that's one thing, right? So this solution, at least, as you said, well, but under what situation you will have both processors, two processes enter the lock at the same time? How could that happen?
Maybe just there are two processors just called the.
You have two processors, right? So first of all, at least we know, but what if I only have one processor? Will the solution work? So we know if we have two processors, it doesn't work, right? What if I only have one processor? Will that work? Okay, Tyler, you raise your hand. What do you think?
I'm also on Team Blue. So there could be multiple processes on that one processor, and based on the the scheduling of the OS, you could have two processes trying to work at the same time, so they both get to the lock. They both get to that.
Well, you only have one processor, right? How
Yeah.
can one processor running two programs concurrently? You only have one program counter register.
Yeah.
Let me explain this.
Sorry.
Okay, if the process 1 executes the while loop, then it has been switched to the process 2.
Okay, cool. Right. So what will happen here is that, right? If I okay, saying that, so the problematic part is this, right? So when I am running the while checking, right? And if the context switch occurs here, the process 1 saying that process A thought I grabbed the lock, but I get context switch out. And in the meantime, another processes also gets switched in the processor, and then it checks the lock. Well, he feel like I can use the lock, right? So both of them turns out that they are in a situation that they thought themselves are both seeing the lock as one. So it turns out that they will continue execution, and both of them will grab the lock, enter the critical section, even though you have only one processor. So Rogelio, do you now agree that even the first case is not working?
I kind of, no, I'm not sure because I'm looking at the textbook and maybe I'm understanding the definition of mutual exclusion. But it's saying that when you so they're evaluating spin lock and it's stating that, it does provide correctness. It provides mutual exclusion.
Right. So, but what I'm telling you is that it doesn't provide correctness. The spin lock doesn't provide correctness, right? If you have context switch occurs in the middle, and as we said, right now, the operating system kernel or the user space has the capability to schedule the thread. It's possible that this switch would occur here, right?
Yeah.
Josiah, anything to add?
I just wanted to ask a quick question. Are there spin locks that do provide correctness and just this one doesn't?
This one doesn't. So this implementation doesn't, right? So now the whole thing is that how can we get this right, right? So one of the solution that you might read in the textbook is saying that let's disable interrupts. Okay, so thanks for all of your inputs. I think we have a pretty good discussion here. So for the previous question, the right answer is E, none of the above, right? And you might saw in the textbook saying that, okay, one of the potential solutions is to disable the interrupts, right? So by disable the interrupt, as we said, right, preemptive multi-scheduling is that you use interrupt, the timer interrupt to change the process, right? So what if now we disable that interrupt when one of the thread grabs the lock? Will that work? All right. Wrap up in 15 seconds. Oops. 5, 4, 3, 2, 1. Time is up. Okay, so so for this question, I do believe we still need discussion. So let me send out the screenshot real quick. Okay, I already sent it out. You should receive it. Go and start discussion. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now for this question, I'm inviting one of the group to share your thoughts with us. Okay, I found Yunze. Hello?
Okay, our group choose E at the end. Because if you disabling the interrupt on just one single processors, it will work perfectly. But if you are disabling the interrupt for multi-processors, it won't work. So yeah,
that's from Team Red, right?
Yeah.
So from the result that I found here, the other group must chose A. So can the other group share your thoughts with us? Josiah.
I don't think we were really thinking too much about multiple processors, but if
he brought up the concept of multiple processor, do you agree that it's all broken?
I think that could be the case. Yeah, we were thinking about a single processor.
Right. So the thing is that, disable interrupts. It would work if you only have one processor. However, it doesn't work in the era of multiple processors, right? So this question, I would say, the answer, unfortunately, it still doesn't work, right? So then you might ask me, okay, so professor, what's the right way of getting it, right? So so the thing is that, okay, so the key thing is that the reason why it's getting wrong is because when you see the lock, you do not update the lock when you see the lock. So the key thing is that you should have some kind of support that you are allowed to evaluate and change the value atomically, meaning that whenever you see it, you can change it, and it's all single operation. So if you really want to have the spin lock idea works, then it turns out that you need hardware support. And here is the hardware support. And that's why being a software programmer, sometimes you still have to know assembly language. So in x86, they provide this kind of instruction, exchange. And this exchange instruction, what it does is that we receive two arguments. And with these two arguments, one is the address, meaning that the place of the lock, and the other is the new value you want to set. So if the new value you want to set, so for here we want to set the new value of the variable, saying that we want to set something equal to 1. If when we try to set the value equal to 1, we change the value, it will return 1 to the caller. Otherwise, it will return 0, or the other way around. So in this way, right, if you are the one who gets to change the value, you grab the lock. However, even though I see the log as a variable that's currently 0, but when I try to set a log, I cannot change the value, meaning that somebody else already changed the log value. Then you didn't grab the log. So that's the whole idea of this instruction, is that if you are the one who really successfully changed the value, you are the only one gets the return value 1. Everyone else would get return value 0. So in this way, only one of them who really changed the value will have the lock. So here's the implementation, right? So if I successfully change the lock, then I can enter the critical section. Otherwise, it won't. I'm still in a situation that I saw the value is not changed, so I will stay in the lock. So if you so here's the key thing, right? So if you really want your spin lock to implement correctly, the answer is that you have to use atomic instructions. And all other implementation without the help of atomic instruction may lead to incorrectness in spin lock. So anything that you want to maintain a shared variable correctly, you have to use atomic instructions. So so in your project, you definitely will deal with this kind of situations. So the reason why I pull this out is because I want you to make sure that you have this idea in mind and you know what's the right time of using them. So in addition to spin lock, we talk about one of the issues with spin lock in your previously, you probably already learned in your undergrad study is that, well, spin lock, because you have to keep checking. So the processor overhead is too high. And turns out that it will create another thing that we mentioned in in this solution is that, well, a thread can potentially be postponed indefinitely because the other thread is spending too much resource in checking the variable, right? So a better solution that we mentioned is actually semaphores. So the basic idea of semaphore is more like a signal. So the semaphore is essentially a synchronization variable, and it's a very powerful tool to implement all types of a critical section problem. Is that in addition to the binary value 0 or 1, you can give the semaphore a value, any kind of integer value, meaning that how many parallelism are you allowing in a critical section. Of course, in this way, you can use semaphore to implement a lock if you only allow one process to be in a critical section. And for our bounded buffer problem is especially useful because in this way, you will be able to allow multiple consumers or multiple producers. So the idea of semaphore is somehow like a signal that your train will see like, okay, if I am allowed to pass this segment of the rail track. So in semaphore, there are two operations. One is semaphore wait, means that it's somewhat similar to see if I can enter the critical section. And if when I see the semaphore value is greater than 0, meaning that the critical section is still allowing process or thread to enter, then you can enter the critical section and decrement the value of S in the meantime. And again, the decrementation should be done with atomic instructions, as we mentioned. And if the semaphore value reaches 0, meaning that no one the critical section is already reaching its capacity, so no one can go in there. However, instead of having everyone spin lock on the S, the semaphore implementation actually puts everyone in a wait list. Instead of, so this is like, okay, so this is something interesting, right? It just happened to me. Like, I think I told you guys on Tuesday that I keep checking the Riverside University Systems website saying that, hey, when can I get a vaccine? And I refresh the website all the time, which consume their web server resource, also waste my time, right? But turns out that they probably already have someone overlook my slides. So today they saw, they sent me an email saying that, hey, please fill this form and you can put yourself on a wait list. So the semaphore idea is pretty much like this semaphore operation in a way that, well, you can go to see the website first, but if the website is saying it's full, okay, sign up on a wait list. And then we will notify you whenever it's available. So when you are done with your critical section, you will call semaphore post, saying that, okay, I'm done. So this semaphore post is will invoke the system facility to wake up one of the process in the wait list. So in this way, because you put your process in a wait list, so as long as you're on a wait list, eventually you will get code. So the semaphore serves as two purposes. One is that it saves the hardware resource. And the other thing that is more importantly, because you have the idea of a wait list. So it also guarantees a fairness because as long as you're on a wait list, and if we can call up this process in order, then everyone would get a fair chance to enter the semaphore protected section. So that's the whole idea of semaphore. So as you can see, the whole idea is that you just maintain the value. But as we said, when you try to increment the value or decrement the value, those must be operated atomically. So the thing about semaphore is that it really helps us to reduce the busy waiting time, and it's easier for programmers. And the most importantly, that you only need to learn this set of semaphore facilities, and it works for lock and it works for all sorts of information. So if I were you, I would not be too sticky about the implementation of lock in a way that I would embrace the idea of semaphore. So now, given that you know the idea of semaphore, right? So I just want to give you an idea that how to use semaphore. So why don't you go through these pieces of a code and tell me how are you going to use the semaphore to implement the bounded buffer problem correctly? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, I would embrace the idea of having you guys go into a short discussion. So go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, I saw we have a pretty good consensus on the answer. So can I have one of you share your thoughts with us? Okay, I have Xing Yun. Xing.
Hi,
Xing
here's
Yun.
Xing. Our
Xing Yun,
answer
okay.
is P because we can know the man's rate is the producer and the child's rate is the consumer. When the buffer is empty, the producer could produce some data and put it into the buffer. And when the buffer is filled, now the consumer could take data from the buffer and use it. And then says
So the consumer should wait on the field, and the producer should try
empty.
to wait for empty entries, right? So that's why in this way, W should be empty and Y should be filled. And then now how about X and Z?
For the month rate, when there's some data was put it into the buffer, and now we can set the semaphore to filled, so the X is filled, and the
X is filled.
same logic is for child too. When we have used the data in the buffer, we can set the semaphore to empty.
Okay,
Yeah.
awesome. Right. So here I think it's sorry. So here I think it's kind of interesting that in the past, if you use lock, you only have a single variable. But now with semaphore, you have to be really careful about thinking that, okay, so like this semaphore wait and this semaphore pause, they are operating on different variables. So the difficulty in using semaphore is that you really need to have some kind of clear mind to make sure that you really know what you are doing. So, and this kind of semaphore programming is pretty interesting. And now I'm giving you a homework, which you will give me your answer in your midterm is that right now, what if you have multiple producers and multiple like consumers, then how are you going to get this code running correctly? Okay, so I'm not going to tell you the answer right now, and you should be able to tell me that in your midterm. So now let's switch to a topic I believe we should already taught you all the necessary things that you should know about the process scheduling and the thread scheduling, including the thread programming. And as we mentioned, right, the whole operating system is to provide a vehicle of virtualizing your hardware. So another big part of our hardware is actually memory. So now let's talk about virtual memory. So previously we mentioned that for process abstraction, right, not only manipulating the processor, it's also important that we have the capability to share the DRAM, right? So, but what's the issue of sharing the DRAM and why we need virtual memory? So think about that, right? You're programming like this, and you have a set of memory like this, and if your memory capacity is big enough, yes, you can accommodate one program. However, what if my programmer developed a program that is larger than my memory? Then can I still run my program correctly without additional abstraction, right? So like if I'm only allowed to directly interact with my physical memory, then my program will be constrained by my physical installation of the NAND memory, right? And another thing is that, okay, even though my memory is big enough, right? Now, we have multiple processors, right? So my program is big enough, my memory is big enough to accommodate one program. But what if I am running a program on another machine with a smaller memory, right? Will that work, right? So one of the interesting things, I remember that I talked to you guys about the Chrome performance issue. So there were ones that I complained to my friend in Google, and I said, well, your browser is terribly slow on my computer. And his answer is like this. Well, his reaction is like this. Hey, well, how big the memory you have? And on my old Mac, I only have 8 gigabytes of memory. And he said, well, you know, every developer in Google, we have 32 gigabytes of memory on our computers, and you should have one of the computer, right? So being a customer, you might not be happy with the answer, right? So the thing is that you actually don't want a program run on one machine, but it doesn't work on the other machine, right? That's not the way how it should work, right? So need some kind of abstraction to at least guarantee that, well, the program will be runnable on the other machine. So like Google's example, even though the Chrome is developed on 32 gigabyte of machine, and it does run on an 8 gigabyte machine, but just slower, right? That's another issue, right? But you know there are something else here to control, to manipulate your memory, to make sure that the program developed on one machine with larger memory size will work on the other machine with smaller memory size. And another thing which I want to say is that, okay, although the memory is big enough to accommodate one program, but if I want to run multiple programs in the same time, right, how can I deal with that? So it turns out that you need a virtual memory abstraction, right? Like previously, we used the process or say the thread abstraction to allow a single processor to run multiple programs. And again, the virtual memory abstraction will allow a single piece of memory to be shared among multiple processes, right? So the basic concept of virtual memory is that we provide a virtual memory space. So when you run your program, your processor is not aware of the physical memory you have. Instead, your program is running in an illusion that the operating system creates. And the operating system, the program only sees the virtual address when you run a program, and ignoring the fact that this address would be dynamically mapped to different location in a physical memory. So that's the whole concept of virtual memory. So if you don't like my 2D representation of that, let me show you my 3D representation of that. So the whole concept of virtual memory is like this. Whenever you run a process, I create a virtual memory abstraction like this, and the virtual memory will contain code section, data section, and static data section, and another data section for your local variables and global variables that is allocated dynamically. And your operating system will, in the meantime, dynamically map part of the virtual memory data to your physical location. So that's the whole idea of virtual memory. So in this way, you allow single piece of physical memory to be multiplexed to different processes. So that's the whole idea of the virtual memory abstraction. So so in this virtual memory abstraction, right? So you can, if you remember the demo that I showed you in the very beginning, right? So for this demo, our outcome is that you will see that different processes, they can run on the same processor, and we know because we have the operating system scheduler, so we can create an illusion that everybody is using the same processor, and we multiplex that. So this is like the Fiona we said in the last lecture, right? So, but on the other hand, right, everyone gets different value preserved, and that's what the virtual memory did for us, right? Even though everyone has the same address for variable A, right? So the concept really happened behind the scenes is that for each process, we maintain some kind of mapping table or mapping mechanism to allow their virtual address to be mapped to different physical locations. So that's the whole idea of virtual memory, is that you create some kind of illusion and the address translation mechanism to map your virtual memory to physical locations. So a lot of you might already know that the basic, the mechanism that we are using mostly right now is so-called demand paging. But before we go into the detail of demand paging, I still want to start from the oldest abstraction that we talk about. That is segmentation. So the basic idea of segmentation is that the compiler will generate the code using the virtual memory address space, and the operating system will partition your physical memory location into segments for each running application. So, and the hardware will dynamically translate the virtual address into physical memory addresses. So conceptually, if you have two applications, or say two processes that they contain, they have a segment starting from 0 to address X, then maybe from 0 to X in a physical memory location will be allocated to application A. And when you want to run application B, the application B will start from X to 2X, right? So everyone will get its own segment in the physical memory location. And what happened in the address translation is that when you are running this processor, running this process on a specific processor, in addition to the program counter indicating where the current instruction is, you also maintain a base register to tell you the starting address of the segment. So saying that if I'm currently running this application, the base register will be set to X, right? And so if right now I am accessing a zeros instruction in this segment, then it will be translated to the address of X, which is the right place of the virtual address mapping to the physical location on the machine. So this translation is simple, right? You only need a base register and the requesting address, right? So if the instruction saying that I want to load 4,000, and turns out that this 4,000 will be at with X, the base register, and it will be pointing somewhere to the segment. But if you are wise enough, you probably already know that this kind of address translation also has its drawback in a way that, well, what if I have a malicious code that trying to give you a negative address and turns out goes this way, right? So what you really need to fix that is that you need a bound register to make sure that you know the boundary of the segment, and you have to check the boundary of the segment, making sure that it's not going over 2X and it must be greater than X. And whenever you have a situation that you are under the value of X and under the situation that you are greater than X but under 2X, then you can proceed, right? Otherwise, it will create an illegal memory address access message called segmentation fault. And since the first lecture and now you see a segmentation fault several times. And the segmentation fault really represent the case in the good old days that if you are using a segment for address translation and if your address is out of bounds. So if you have a memory address gets translated, it turns out that it falls in this place or this place, we see a segmentation fault, right? So that's why I have to tell you about this. Otherwise, you probably don't know what I'm talking about in the opening video. So that's a whole story about segmentation fault. Although right now you might know that, well, so seg fault is actually the case where, and we still use the term segmentation fault to refer to memory protection all the violation of memory protection all the time, even though most of the time our system is not using segmentation anymore. So that's the most important thing that you need to know. What is segmentation fault here? Okay, so given that we have introduced the idea of segmentation fault, and I think we are pretty good to go for the next week in talking about virtual memory. But before we finish the lecture today, there are still a few things that I want to let you know. So first of all, reading quiz due next Tuesday, and I changed my office hour because I found the Monday office hour time, nobody tried to use it. And I will separate this two office hour to be 3 p.m. to 4 p.m. on Monday and Thursday, 9 a.m. to 10 a.m. And it should work out pretty well for all the time zones. So let me know if you need assistance, spatial assistant for an office hour, because I do believe sometimes you need an office hour to talk with things directly. And project has been released and due in about a month, as we said. And I had some change this morning because some of you already reported some issues in the benchmark. Rogelio, do you have any question?
Yes. For the slides, they're different. The preview slides are different than the ones on lecture. Are they updated after lecture on the
The
website?
previous slide will not be updated. I
Oh, okay.
am giving you the lecture slides.
Oh, so
So the
like
preview
there's
slide is only for you to preview the material. And like the content today, it's because we are falling behind our schedule. So the content, the preview slide today is on virtual memory. So the next Tuesday, you will use that preview slide. But for the content today is actually covered in one of the early preview slides that we had.
I see. I
Yeah.
guess let me rephrase my question. The slides you use in lecture, are they ever posted after lecture?
They are always posted after lecture. So you can check the website. They are always there.
Okay, so they're the updated
Yeah.
versions are there. Okay.
No. So I have two columns. One is the slide for preview slide. One is the column for
Okay.
preview slide, and the other is the release slide. And
That makes
the
sense.
preview slide is only for you to take notes, and it doesn't mean anything. The official slide is the release slide. So it's like the beta version and the release version. And the release version is always the most authentic version, and it's always the most reflective version to the lecture content.
Thank you for clarifying.
Okay, makes sense. All right. So so project that's important, and try to make sure that you pull out the latest change whenever you see there is a change, and watching it is probably a good idea. And well, some of you are asking about the midterm. So the midterm again is scheduled in a period of time, and they cover the material up to February the 9th. And if you don't think you can start the midterm immediately after the lecture, no worries. You can take whatever time you need. Just make sure that you complete and submit your midterm before February the 15th. Other than that, enjoy the rest of your week, and then I will see you next Tuesday.